So to go ahead and do this problem, we have a position function, and then we want to label the velocity function. So position is related to velocity, and that velocity is the derivative of position. So this would be velocity, and our units would be meters per second. And we would still have time on the horizontal axis. And since velocity is the derivative of position, it is the slope. So if we look at this graph, on the time interval 0, 2, this graph goes up 4 units, so its slope is 4 over 2, so n would be 2. On the interval from 2 to 4, our graph is horizontal, so it has slope n equals 0. And on the interval 4, 5, our graph goes down 3 units, so it has slope negative 3. And then lastly, we go over 2 and up 2, 4, 6. So then here we would have slope, what did I say, 2, 6 over 2, so that would be positive 3. So if we graph our function, it would look something like this. So we'd have a piecewise function that looked something like this. So to make a connection to something we've been working on a little bit later, if I were to make a square, what's the area of that square right there? Well, it's 2 by 2. So then it would have area 4. And when we get to this coordinate, what is the coordinate of that point? 2, 4, right? And then if you added the integral, it would be 4 plus the area under the curve here. Well, the blue part has no area, so our y value stays 4. And then our area here would be below the x-axis, and that would make it negative. So this would have area negative 3. So our total area would be 4 plus 0 plus negative 3, which would give us, at this point, 5 and 1, because 4 plus 0 plus negative 3 is 1. And then lastly, the orange, if we made it into a rectangle, 2 by 3 would have area 6. So then we get up here, and 6 plus 1 gives us 7, which is that final ordered pair. So if we integrate, it gives us the y-coordinate, or the value of the original function at that point. So this is just further illustrating the idea that if we take the derivative of something, it gives us the slope, and if we integrate the slopes, it gives us back the original function, i.e., Fundamental Theorem of Calculus Part 1, derivatives and integrals undo each other. So that is question number 1. So it turns out there's a couple of different ways that we can do this. The classical way that we learned back in Chapter 2 is that we would factor, and that would factor into x minus 4 times x plus 4 all over, and then we would have x, we need factors of 8 that add up to negative 6, so that's negative 4 and negative 2. And then the x minus 4's reduce out. And so now it's continuous, so we plug it in. 4 plus 4 is 8. 4 minus 2 is 2. And 8 over 2 gives us 4. But we could also notice that this is type 0 over 0. Because if I plugged 4 in, I would get 16 minus 16. And if I plug, which is 0, and if I plug 4 in here, 16 minus 24 plus 8 is also 0. So by L'Hopital's rule, this is the same as the limit as x approaches 4 of 2x. So we take the derivative of the top, and then 2x take away 6. And now we plug in 4. 2 times 4 is 8. 2 times 4 is 8 minus 6 is 2, and we get the same thing. So honestly, I think they're about the same amount of work factoring or taking the derivative either way, but what do we end up with? 4, right? So we've learned a whole bunch of different ways to get from A to B, so keep those in mind as we move forward. All right, so to use Newton's method on this problem, we identify that our function, since it's already equal to 0, is going to be sine x minus pi over 12. And then its derivative, f prime, is going to be the derivative of sine is cosine, and the derivative of a constant is 0. So then our formula is x to the n plus 1 is equal to x to the n minus f of x sub n divided by f prime of x sub n. So there's a couple of ways we can do this, but let's just plug everything in. So we would have x to the n plus 1 is equal to x to the n minus, and then we have the sine of x sub n minus pi over 12. That's our f, divided by f prime evaluated, so the cosine of x sub n. So now that we have this set up in our calculator, we're going to replace all of the x sub n's with an answer, and we're going to use our initial guess as x1. So we're going to do 0. We're going to save 0 as our answer. So to do that, we just press 0, and that puts that in as our answer. And then we type in our formula. So it would be second, and then we use the minus key down here in the bottom corner. We have answer minus, grab our fraction, the sine of the answer minus pi over 12, and then the cosine of the answer. When we press enter, that gives us x1. We press enter again, we get x2, x3, x4. And we notice after x4, it actually doesn't change. So x4 and x5 are exactly the same thing. And that gives us the value, or the approximation, of the 0 of that function. So it would be 0.26488647. So if we wanted to find the derivative of this, we want to use the fundamental theorem of calculus part 1, which says that the derivative of the integral from a constant to x of f of t dt is equal to f of x. But we don't have that. First thing we notice, our lower limit of integration isn't a constant, and our upper limit of integration isn't just x. So it's not just like this, f of x, it's f of something. So this, in our case, we have composition. So the first thing we need to do is use the integral property. So we have the property that if we have the integral from a to b of f of t dt, that is equal to the integral from a to c of f of t dt plus the integral from c to b of f of t dt. So we can break up an integral by putting the same constant in between those two things each time. So in our case, we could rewrite f of x as the integral from sine x to some constant c of the natural logarithm of t dt plus the integral from that same constant c to the natural logarithm of x of the integral natural logarithm of t dt. Okay, so now we're getting closer to what we have. So on this next one, we also need to use a property of integrals. So use the property of integrals that if I have the integral from a to b of f of t dt, that is the same as the negative of the integral from b to a of f of t dt. That is, we can reverse the upper and lower limit of integration, but if we do, it changes the sign of the integral from positive to negative or from negative to positive. So then we would have f of x would be equal to the negative of the integral from c to sine x of ln of t dt plus the integral from c to ln x of ln of t dt. So now lastly, both of these are function composition. So if we look at this and we look at this, they're both function composition. Here we're going to have u is going to be the same as sine x, and in this one we also have function composition. And I'm not going to use u again, I'll use v, and my function composition is v is the natural logarithm of x. So then finally we end up with f of x is equal to the integral from c to now just u of ln of t dt plus the integral from c to v of ln of t dt. So now to do this, for each of them, it's going to be the fundamental theorem of calculus plus the chain rule. So when we find our derivative, we're going to have f prime of x is going to be the natural logarithm of u times the derivative du dx. So the derivative of u is going to be, so our u is sine is going to be cosine x, then plus we're going to have the natural logarithm of v, that's the fundamental theorem of calculus part 1, times the derivative of v, so the derivative of the natural log of x is 1 over x. So these parts right here are FTC part 1, and these two guys come from the chain rule. Because it's df du, du dx, df dv, dv dx, and then we finally back substitute everything out, and we get f prime of x is equal to the natural logarithm of the sine of x, because u was sine x, times cosine x, plus the natural logarithm of the natural logarithm of x, because v is ln x, times 1 over x, which will give us this. And that would be our f prime. So that one was pretty difficult because it required us to not just use the fundamental theorem of calculus, but it required us to use some of our properties of integrals. So we first had to break the integral up from 1 to 2 different integrals, and then we had to use some of our properties of integrals that if you reverse the limits of integration, then that will change the sign of the integral, and then identify the function composition so that we could use the fundamental theorem of calculus connected with the chain rule to finally give us our solution. All right, so to do this question, we need to use implicit differentiation. So we would take the derivative of both sides of the equation, so that's d dx of 2x squared minus d dx of 6y squared is equal to d dx of 11. So the derivative with respect to x of 2x squared is going to be 4x minus the derivative of 6y squared is 12y, but we're differentiating y with respect to x, so we get a y prime is equal to d dx of 11, which is 0. So now we just need to solve this equation for y prime. So we add 12y, y prime to both sides, and that gives us 12y, y prime is equal to 4x, and we divide by 12y, and we divide by 12y, so finally our derivative y prime is equal to, 12 goes into 4 3 times, so x over 3y. And that would be our solution to that differentiation problem. All right, so to calculate this derivative, we're going to need to use the chain rule. So we have y of u is going to be u to the 10th, and our u is going to be x squared minus 6x plus 9. So then y prime is dy du times du dx. So dy du is going to be 10u to the 9th times du dx is going to be 2x minus 6. So then substituting back in, we have x squared minus 6x plus 9 times 2x minus 6. I'm missing my 9th power there. There we go. And that would be our derivative of this. All right, so we want to find the horizontal and vertical asymptotes of f of x equals the square root of 4x squared plus 1 all over 3x minus 5. So to find our horizontal asymptotes, we need to recall that the horizontal asymptotes are the values of the limit as x goes to positive infinity and negative infinity. So if we want to find the horizontal asymptotes of f of x equals the square root of 4x squared plus 1 over 3x minus 5, we need to take the limit as x goes to both positive infinity and as x goes to negative infinity. So let's start with the limit as x goes to negative infinity of the square root of 4x squared plus 1 all over 3x minus 5. So we factor out the highest degree from both the numerator and the denominator, and that gives us the limit as x goes to negative infinity, and we're going to have x squared in our numerator, which is then 4 plus 1 over x squared, all divided by, and then we factor out an x from the denominator and gives us 3 minus 5 over x. And then we focus on this piece right here, and we have the square root of x squared, and it's important when we're taking limits, especially if we're going to negative infinity, to recall that the square root of x squared isn't x, it's actually the absolute value of x times the square root of 4 plus 1 over x squared all over x times 3 minus 5 over x. So now we're going to need this again, this piece specifically when we go to positive infinity. But if we recall, the absolute value of x is equal to negative x if x is less than 0, and it's equal to x if x is greater than or equal to 0. Because if we check this, if we say negative 5, a minus minus 5 makes it positive 5, which is what the absolute value of x is. So since we're going to negative infinity, we're going to use this branch. So then we're going to get the limit as x goes to negative infinity, and we're going to get negative x times the square root of 4 plus 1 over x squared divided by x times 3 minus 5 over x. So then our x's are going to reduce out, so x and x, and then as we go to positive or negative infinity, this goes to 0 and this goes to 0. So then our limit becomes the negative, and then we have the square root of 4 over 3, and the square root of 4 works out nicely to be 2, so we get that our limit is negative 2/3. So then similarly, this is the horizontal asymptote, or one of them, is y equals negative 2/3. And if we take the limit this time as x goes to positive infinity, bringing this piece down again, only thing we're changing is we're going to positive infinity this time, we still have the absolute value of x, square root of 4 plus 1 over x squared, all divided by x times 3 minus 5 over x. But since we're going to positive infinity this time, we're going to replace, and positive infinity is bigger than 0, we replace the absolute value of x with just x. So we have the limit as x goes to positive infinity of x times the square root of 4 plus 1 over x squared divided by x over 3 minus 5 over x. And once again, our x's reduce out, and this goes to 0 and this goes to 0. So then our limit this time is the square root of 4 over 3 and is positive 2/3. So we have another horizontal asymptote, and this horizontal asymptote is at positive 2/3. All right, so now we go back, and the original question asked us to find the horizontal and vertical asymptotes. So we have our two horizontal asymptotes. The vertical asymptote So the vertical asymptotes are the x values where the limit as x approaches a from the left of f of x, or the limit as x approaches a from the right of f of x equal positive infinity or negative infinity. This is often anywhere where the denominator is equal to 0, because if we have the numerator as a constant divided by 0 is going to be infinity. So we have our f of x was the square root of 4x squared plus 1 all over 3x minus 5. So we're going to have our 0 of the denominator is going to be when 3x minus 5 equals 0. So we add 5, we add 5, we get 3x equals 5, divide by 3, and we get x equals 5/3. And if we check, the limit's going to be both positive and negative infinity depending on whether we come in from the left or the right. So our vertical asymptote is x is equal to 5/3. So vertical asymptote's 5/3 and horizontal asymptotes are y equals negative 2/3 and y is equal to positive 2/3. And that's all of our asymptotes for that function. Evaluate the integral 3x squared minus x all over the square root of x dx. Alright, so to evaluate this integral, we first need to use some algebra. So if we do termwise division, we can write this as 3x squared over the square root of x minus x over the square root of x dx. And then use the fact that the square root of x is x raised to the 1/2 power. So then we would have the integral of 3x squared over x to the 1/2 minus x over x to the 1/2 dx. So then we have two things with the same base, so we subtract our exponents, so we get the integral of 3x to the 3/2 minus x to the 1/2 dx. And then we now can just use our power rule for integrals, so we add 1 to our exponent and divide by it. So we have 3/2 plus 1 is 5/2, and then we divide by 5/2 minus x. We add 1 to 1/2, which gives us 3/2 divided by 3/2 plus c. And then we simplify that up a bit by multiplying by the reciprocal, and we would get 6x to the 5/2 over 5 minus 2/3 x to the 3/2 plus c. So the key here in this problem was using algebra to rewrite this rational expression as some single terms and converting our radical into x to the 1/2. Alright, so the key idea for this one is we need to use a trigonometric identity, so we need to use the double angle identity. Which is that the sine of 2x is equal to 2 times the sine of x times the cosine of x. So if we substitute that into our integral, we get 2 sine x cosine x all over 1 plus sine squared x dx. So then we let our u equal the entire denominator. So u is 1 plus sine squared x. Then du, derivative of a constant is 0. The derivative of sine squared is 2 sine x times the derivative of the inside, which is cosine x dx. And we divide by 2 sine x cosine x. And we divide by 2 sine x cosine x. These reduce out, these reduce out. So then finally, we substitute all of that into our integral. So we have 2 sine x cos x all over u times du all over 2 sine x cosine x. And then a whole bunch of stuff reduces out, which is super nice. And at the end, we have 1 over u du. And the integral of 1 over u is the natural logarithm of absolute u plus c. And then our u is 1 plus sine squared x. So we get the natural logarithm of the absolute value of 1 plus sine squared x plus c. And that would be the value of that